Hi everyone, this is continuous with the XAI series, and today we are going to be looking at the line classification model that will be actually explaining the decisions made by the model through the line library. So, I will be referring to this particular blog post on the towards data science for the Lime explanation. I will also put a description of this link in the video description, so that you can also see this particular blog post, which clearly explains that how the Lime works. For the brief, I can actually explain a bit that the Lime actually trains a small local surrogate model on the global model for a particular instance, so that you can get a linear line for that particular instance, and you can explain the decisions by the weights you got by of this particular line. So this is the basic principle of this line, and this works for all the models because it is model agnostic technique. And the line also works for the text and also for the images and also for the tabular data. So we can use it for any purpose. In this particular blog post, they have used Lime for image data. How this is actually used for image data is that, let me actually briefly explain the process of the Lime working. So firstly, what line does is that it actually makes more points around this particular local instance which we have to explain. So let me actually define first the objective, that what we are actually trying to do. We have got a classification for a particular local instance, and we want to know that why that particular classification has been made for that particular instance by the model. That what's the hidden thing inside the model that is actually predicting the class to be something and not the other one. So we have got to know that by using the linear models we can actually get the weights directly, and by looking at the weights we can get to know that which particular feature is actually forcing the output to be in one direction rather than another. By looking at the weights we can actually get that. So the Lime actually use that technique. So it actually explains that local instance by constructing a local surrogate model means a linear model around that instance, and then actually get the weight, and then through the weights it actually explains. Now, in the case of images, we don't have tabular data, so it actually it actually perturbates many images around the local instance. For example, if we have to explain this particular image, then we will create more images by switching off and on the pixel values and creating more images, and then it will actually catch the different predictions for all those images, and accordingly like this, and it will catch different prediction for all those images, and then in the end it will actually get to know that which pixels were the most preferable for a particular class. So this is how Lime in brief explains the decisions, and they were also given the code, so we will try to run and explain the code. Okay, so this is particular implementation of the Lime with the Docket Panda dataset. You will find the dataset on the internet very easily, as I think on Kaggle or say other websites also. So you can download that dataset, and it is also available as a link in this blog post, so you can go ahead and download it. Now while I'm using Google Collab, and one problem arises in Google Collab is that you need to again and again upload your files here, which actually doesn't fit well. So for actually removing this particular hindrance, what we can do is that we can actually upload our data set on the Google Drive and then mount Google Drive here by using this particular option. Where is the Google Drive? Yes, here is the particular option. My Google Drive is already mounted. And then you can use your data set from your drive. That is, you will upload the zip on your drive, and then you can just unzip with this particular code from the Google Drive, so that it actually gets into the content folder which is actually present here. And then from that content folder you can actually access your data. Right, you will find the content folder into your Google Drive itself, in which your things will be unzipped whenever you are actually trying to access your unzipped data. So firstly what we are doing is that we are just importing all the libraries needed to develop the model. So we have actually imported many layers. So what we are trying to do is that firstly we will create an artificial neural network model, which is actually a custom model made by us by using our own layers, and then we will also import the pre-trained model into it, and we will compare. That model also has a class of panda in its classification output classes, so we can use that to actually classify a particular image of panda, and then we will just compare the predictions for both the models, and also will compare the pixels at which the models have looked by using line for the particular prediction. So this is the main aim or objective of our today's video. So here we have imported all the layers which are needed to create a sequential model from tensorflow.keras.layers. We have imported all the layers. And we have import from the models, we have imported the sequential and the model which we will be using, and then we have the Adam, which is actually used while compiling the model. So we have different options available out there, but we will use the Adam, and then from the pre-processing we are actually importing the image data generator and the directory iterator. So image data generator does what is that in the case of images you used to have small number of images which are actually not sufficient for training a model. So what we actually used to do is we used to use computer graphics, and then we used to kind of say shift the images by some amount, or say crop the images by some amount, and we need to apply we used to apply some filter on the same images, and we used to rotate the images, and we used to get different samples of the same image, and then through all those images we used to actually train our model. So for that we already have a library in the Keras, which is actually image data generator, which does this purpose. And the directory iterator is the iterator which actually iterates over our directory to get the original image, and from those images it actually generates the sample images by applying some computer graphic operations. Okay. Then we have also imported the MNS, and then we have NumPy and all other libraries, and PyPlot for just printing the images here in Collab. We can use the PyPlot for that purpose also, and also you must know that PyPlot is already used for figures and say graphs already. And then we have the mpimg just for the conversion into another sizes, and all those purposes we are importing all these libraries. Now we have also imported the OS just to actually do the operation like this one, that is, this is the directory from where we are actually getting the samples of the original images after unzipping our file. So let me actually run this. Right, this is run. Now let me run this. So this will actually unzip. Okay, from with a zip file, there's a module for a zip file. I'm actually importing the zip file zip file class, and with this we can actually unzip some of the content. So I have uploaded this particular file in my Google Drive, and thus I can actually go to my Google Drive and then unzip this with this particular code, and this will be extracted here, and after it is extracted it will print completed. Now I can actually I must need to first traverse my directory structure, and I need to find the particular folder in which I have 3 class images folders. So as mentioned in this particular blog post, I need to have this particular directory structure, that there is a upper parent directory and we have subdirectories in which I have further images of the respective classes. Like for the dog folder, I have all the images of dog. For the cat folder, I have all the images of cat, and for the panda folder, I have all the images of panda. So what I found is that the data set has been actually a bit updated, so you need to find the particular directory by yourself. So I found that it was in the animals, and in there is another subdirectory called animals, and in that I found those 3 particular folders for actually getting the data for the train and the test. So let me actually try finding. This is my drive. Okay, so this is just a sample data. Mm, just a second. Okay, so it has been actually extracted here in the root directory and before the drive. So you can actually see that firstly you have a parent directory called animals, and then you have the subdirectory called another animals, and in that directory you have the cats, dog and panda as the three folders. So you want to actually copy the path of this file, and if you actually right click on it, and then you can actually copy path, and then you will see that your path has been copied like this. So these all are actually contained in the content folder, so you can actually consider this particular root folder as the content one in the Google Colab. For other notebooks it might be different. Okay, so firstly I need to generate a training dataset. So what is the approach used here is that you used to actually perturbate the random samples from the original dataset. So you actually use an image data generator for that, and you actually supply all the options for the transformations which will be applied for the images and all through this train data gen etc. Dot flow from directory, and then here you will apply all the settings and all. So firstly you will actually instantiate an object of the image data generator with the rescale value, that is you want to actually rescale it to say black and white. And then you can actually specify the validation split, that is actually your train test split. It means that you want to split into 80% of the training data and 20% of the testing data. Then you have the train generator, which is actually train data gen dot flow from, which is actually your object which you have instantiated a moment ago. And then you will use the flow from directory option with the target size of this, that is you want the images to be in this particular size, and these batch size are for the training purposes, for so leaving for now. And then you have the class mode for categorical, means you have categorical data in the output classes, means categorical values, means you have many classes for those. And then you have set the shuffle to false, which is another parameter, and then you will supply that this is the actual subset for training. And then you will actually another instantiate another object in the similar manner, but here you will actually supply the subset to be validation, that is you are actually instantiating an object for the testing purposes. And then like what you used to do in other models, you will actually get the train and the test values of the x and y respectively by using the next function. Next will actually generate the next sample from these particular source images by applying all those operations. So these are all random at every time you run, so it will actually get you a whole set of samples in the train and the test. Now now you will just need to fix all the file paths. So you just it actually by default generates this type of slashes, but you need to actually replace it with these slashes for the correct path. So just you will actually just replace that, but okay, and then you actually can actually it will actually show you that how many images it has generated in real for now for these particular classes. So you can see that for the image, for the training images you have 2400 classes, 2400 images, and for the testing you have 600 images. Now you are actually creating your model, right? So you have imported the sequential from the models of the TensorFlow and Keras library. So you can actually see that firstly you have a convolutional layer, and then you have another convolution layer, and then third one, and then you have a dense layer. right? So as you might be knowing that the convolution layer are actually used for extracting out the features. What they used to do is that they actually create a filter of the random pixels, right? You have a filter of random ones and zeros, and then it actually gathers the different values from your images. For example, a filter applied to an image can actually get the edges, and another filter applied to the images can actually detect some other features. So convolution layer does what is that it actually creates it actually gathers some feature values from a particular image in a different manner. That is, you are actually trying to look at the same image in a different manner, and that's what a convolution layer does. So convolution, you actually I can actually present this concept in another video, that there is a convolution layer which is actually followed by a max pooling layer, which actually pulls out the feature value in the abstract manner from the convolution layers. There are many convolution layers, and from those all you actually extract out the max pooling layer, which actually comes up with next layers, next values of next matrices as its output, and which actually is feed it into another convolution layer. And then you have the next one and next one, and then you actually apply some flatten layer, and at the end you actually apply dense layers. So dense layer are actually the normal layers which are actually used for the ANN itself, but here we are actually creating a CNN. So we need to first apply some of the convolution layer in the start, and then you actually supply the dense layer at the end. And you can actually notice that this dropout value is actually for the regularization parameter. Now we also want that our neural network, or say convolution neural network, does not overfits to our training data. That is, it is also good that network actually learns a lot from the training data set, but it is also not good that it is restricted to the training data, but not actually gathers the general pattern from the training data, which is also bad. So to actually remove this particular problem of overfitting, we used to apply the dropout layer of 0.2. Dropout of 0.2 means that it will actually just remove the 20% of the features from the previous layer. Means it will leave the leave those features from the previous layer which are not important, and it will not consider those, and it will actually cease to less overfitting probability. Now you can actually see that here you are able to see that it is actually 3 cross 3 something mentioned. So 3 cross 3 is nothing, just the filter size, and the filter is actually a matrix of random 1 and zeros. Now you have the input shape of 100 into 100 into 3. Now what is this? And now you can see that 100 into 100 into 3 means that your image was of 100 cross 100 pixels, and 3 are for input channels, that is RGB. Okay, so now you have a max pooling layer. So there is a bit of calculation behind the scenes for all these, that what is must be the max pooling layer, size after if you have a convolution filter of size 3 cross 3, and there is a bit of calculation for that, but we will actually go for that in the next session. So you can actually see that 16 here represents the number of the convolution layer, means you have 16 of them here, and then you actually use the next one. Okay, so not 16 of them, there are actually particular subsets, means kind of say neurons, which actually and you actually notice that this value must actually increase one after another and not decrease in order to create a good model. So if you are using like what you have used in the neural network, or say ANN, you actually use the number of the neurons there. That is, if you have used the 16 as the previous layer as the neuron number, then you must use double in the next layer, or maybe the same value but not lesser. So that's actually the trend which is actually followed in the CNN also. And in the final layer, always used to be a dense layer, which is actually a 3 output layer, because you have 3 output classes in the final layer, that is dog, cat and panda. And then you are using the softmax. If you had the 2 classes as the output, that you might have used the sigmoid function also, but here you have 3 classes, so you are using softmax. And there are different activation functions like the ReLU or the sigmoid. So what ReLU function does is that it actually takes the negative ones. It actually is kind of a mod operator that actually makes the negative to positive, and it keeps the positives to positive itself. So it's actually kind of a mod function, and sigmoid is kind of a S curve which actually gives the value, which actually contrasts the value between 0 and 1. Now you need to actually compile the particular model. So let's actually also run this. So this is actually run. So yes, let's actually run this. And then after it finishes, let's actually run this particular section also. Now this is particular one which is actually for starting out the compilation of a model, and this will also start the training, which is actually a fit function which you have seen in many models. So what compile does is actually supply the parameters for your model, that what will be the parameters on which you will actually train your model. So this is the matrix which is actually accuracy, which will be shown on every step, and that will be the matrix for evaluating a model performance while training. And then you also supply a loss function, that is there is a categorical cross entropy function, and there is another sparse categorical entropy function which you can supply in this particular option. And then you have the atom optimizer here, right? And then in this model load fit function, you actually supply the training data. So here you are actually supplying the object of the train generator, which actually is supplied here in the model dot fit, that actually says that this is the particular object from where you will gather the data. So every time the train function runs, every time the train function runs, it actually wants some of the data to actually flow into it, so that it can actually train the model. So it will use the train generator here, and here the epochs, which actually are the kind of say number of iterations for the model training. So we have supplied the 80 epochs here, right? And verbose is equal to 1 is that you want to actually get the intuition about what is happening every time the training is done. Means it is actually an option for printing out these particular values on the screen, so that you can actually get the idea about training. So this is just verbose, like you might have seen in Android Studio. There is an option for verbose for just debugging purposes. So yes, before starting training, let's actually recheck that our runtime is runtime is GPU, because Google Collab actually offers us a runtime of GPU for free, so you can use it for faster training. Otherwise, it will run on normal CPU, which is actually really slow. So we will use GPU, which is actually a lot faster than on the CPU. So yes, before okay. So it is already mounting, but one thing to notice is that we need to also run all the cells again if we are actually changing our data. So running it. Yes, running, and this session is also running. And then next, model sequential, and I'm gonna start training like this. So if it compiles well, our training will actually start. So yes, epochs 1 out of 80. So yes, training has been started. So in the meantime, the model actually trains. We can actually have a look at our further code. So yes, what our next aim was that we were also trying to compare our own custom convolution neural network with the pre-trained Inception V3 model, which is actually available in the TensorFlow.keras.mod applications particular folder, or say you can say module. You actually need to import the Inception V3, and you will actually just use a alias for INCnet for using it with that particular name. Now for this particular model, Inception V3, we are actually trying to predict this particular image. So we can actually have a look at this image that we are actually trying to predict the class of this image. So this is that particular panda image which we are actually trying to predict the class for. So there is a function here which actually just actually transform that particular image into a particular format that is compatible to be for the prediction. So we are actually just transforming it into that particular format. What we used to do is that we used to first get the image by using the imread function. Imread function is actually inside the SKI image. SK image means SK image is actually a module in which there is a sub module called IO, and you have the imread function in it. And then you have another function which is actually resize, so you can use those for resizing your image into particular one. So as you know that your model has been trained on 100 cross 100 size, so what you used to do is that you will resize this particular image into 100 cross 100 dimensions. So with this resize function, you will supply first the image parameter, that is here it is your image, and then you will supply the 100 cross 100 as your image dimensions. Now you need to convert the image to an array so that you can actually fit it into the model. So you will use the image to array function, and you will supply the image object here, and then you will, in the similar manner, you will just transform and return this particular image. Okay, then you will get the image here, and then you will try to predict this particular image. Now as we know, okay, so firstly what we are doing is that we are actually predicting with our model the class for this particular image, and then we will use the Inception V3. So this model is nothing but our custom model, and we are using the predict function to actually predict the image for this particular class. Class for this particular image, sorry. And then we will use the np.argmax function for actually getting the class. So what argmax does is that, in simple sense, argmax actually gets you the index in the sequential manner of the particular class which is actually having the highest value. So you know that your 0th class will be what? Cat, and then you have one class for the panda, for the dog, and then you have the 2 number for the as a class for the panda, right? But why is it is that? Because you can see that in it actually takes the number to be in alphabetical ascending order. So you can see that C comes before D, and then the P comes after D. So you have an order of 0 for the C, and the 1 for the dog, and 2 for panda, right? So in this way you will have these particular ones, and in the prediction you will get that particular value, that is the index value of the highest outputted class. So the class which is actually having the highest value will be your prediction, right? So yes, and you can also get the percentage on which it is actually arriving for that particular class, right? So it might be the case that for other classes it was actually getting even lower percentage than this, so that's why it was actually predicting it to be panda. For example, we might have the other percentage to be like 0.10% or maybe say 20%, and this was coming out to be 0.53. So it was actually having the highest value, and that's why the image was a panda. Now okay, so this was actually another one which I tried. Now we have got the prediction, so it's our curiosity now to actually look at the pixels which actually contributed a lot to the panda image, right? So what we will do is that we will install Lime first. So what for installing any package in the Google Colab, what we used to do is we will supply the pip install with the package name, and what you also need to focus is that you used to use the not operator in front of pip, so that it will run it on the command line, and it will download all the packages which are actually necessary for Lime. So after downloading Lime, you can actually import it from the Lime. You can import the Lime image, particular subclass, that particular class for actually explaining the decisions made for the image dataset. And then you can actually get the explainer instance by using the Lime image dot Lime image explainer. And then you need to also supply the image for which you want to actually get the prediction for. So here you will actually supply first the image, and then you will supply the model. Firstly you will actually supply the image, and then you will supply the model. So you will supply the model dot predict function, and your model is the convolution neural network, and you will supply with the predictor function that will actually predict its class. And then you will actually say that you want to actually get from the top three labels. And these are other options which are actually necessary for Lime, like this one, that is the number of samples is equal to 1000. So what this does is that I've actually explained you a bit earlier that Lime does what is actually create the random perturbations around that particular image by switching off and on some pixels to actually get the predictions of each particular random perturbated image. And by looking at those images, it actually have a look that these particular pixels were the most relevant for the output prediction. So it actually gives you the explanation. So here you are actually supplying the number of samples to be 1000 to actually gives to actually create the 1000 random perturbations for the explanation, and get the explanation for all those images to get the highest rated pixels for the output class. So let's actually have a look if our training is finished. So it is actually at the 49th epoch, and it need to perform the till 80. So it is already really fast if you will consider with the CPU performance. So here is our Lime. I think it is actually already installed. If not, we will install this. And then we will get the, but I can only perform this particular section after our image is after model is trained, because it is actually using model as its parameter, which is actually not available now because our model is not trained yet. Now from the sky image, we are using a segmentation module to actually mark the boundaries, right? Like this one, we actually want to mark the boundaries for this particular one, because we already know the pixels which are actually there for which are contributing highest to the output class prediction. So we need to mark the boundaries. So we are using the mark boundaries as the particular function for those. See here we are using the explanation. So explanation was actually the instance from the explainer.explain instance function, which is actually a Lime function, and we actually are using that particular instance for getting the image mask. So firstly we are actually just applying these particular parameters. Yes, these are the parameters which actually says that you want to actually get the positive pixels only, and you want to get the positive pixels only that are actually contributing to positiveness of that particular class, means contributing towards that particular class, means in support of that particular class. So you actually get two results from this particular function, and that is actually temp in the temp, and another is the mask. So you can use a mask for actually outlining those particular pixels and separating the positively contributing pixel from the negatively contributing pixel. And you are getting the negatively contributing pixels from this positive only equal to false attribute, and the hybrid is equal to false attribute. And then you will actually use the pyplots plt alias to actually plot this particular image. So what you will do is that image, you will use the temp and the mask variables which you have got here to actually just show all those things here. So firstly you are actually showing the image with the boundaries of the temp 1 and the masked one, and then you are actually showing another image on the same one, means you are actually showing another axis, means another section here with the other values, or say other variables that are actually stored in the temp2 and the mask2. and then you are just switching off the axis because you want to actually just print the image and not the axis there, because it is not a graph. So now what you actually using doing is that yeah, in the Inception V3 model, what you are actually doing is that from that Inception V3 model you are actually trying to predict the class for the same image. So here we are actually supplying the URL. So yes, we have actually supplied the URL. So image Inception V3, and you are actually again importing the sky image, SK image, for actually doing all the operations on the image transformation, so that it is actually compatible to the format to be inserted into the Inception V3 model. So firstly you need to instantiate the Inception V3 model. You have already imported that model with the inc underscore net name, and then you will get the instance by the Inception V3 class here. And then what you will do is that you will get the you will first need to actually, you will get the results by using this, right? You will get the results by using this particular function, transform image fnori, right? You will supply the URL for that, and URL is still same, that is the same image here of the panda. And then you will just firstly read that particular image by using the imread function as we did in previous one, and then you will resize it to the 299 cross 299 dimensions, because it is actually the Inception V3 actually takes this type of dimension as an input. And then you will just supply some other options so to make it compatible with the Inception V3, and then you will predict the output of this particular one by using that same predict function, but now on INET model, which you have instantiated there. And then you can actually decode the predictions, and then you will print all the predictions by using these functions, that is decode prediction, which we have imported from keras.application.image.utils, right? And then you will just decode those predictions, that for which class it is actually getting which values at the percentage. So we can actually have a look that these particular classes are actually having these values. So the giant panda must be a class in the must be output class for the Inception V3. So it is actually getting the highest prediction for that particular class, so it is actually predicting it to be a panda. So next we want to also actually get the image boundaries and all the explanation for this particular class. So we are actually trying the same stuff here, which is actually the lime explanation for this model now. So earlier we have actually earlier we have actually supplied those particular ones. So lime explanation is actually there for this particular one, and we are actually supplying the same features or say same attribute, but one thing has changed, that instead of this that model dot predict, now we have supplied the inet underscore model dot predict function, because earlier we were predicting with the with our model, but now we are predicting you can see that earlier we were predicting with our model, but now we are predicting with the Inception V3 model. Now we are doing the same thing and same stuff to actually show the different stuffs, and we are actually showing the different boundaries and on the section which are positively or negatively impacting those. So these are the particular features which are positively impacting that particular prediction of giant panda, and the negative pixels are actually not shown here. So there are no negative pixels, and that's all the basics of the lime explanation for the image dataset. So if our model is trained, we can actually have a look at those things by running that. So this particular section is already run, so I can actually run this particular section now. So it is just importing the Inception V3, but I think we must import it in later on whenever we are actually using Inception V3, but it's okay if we are importing it early also. Now it was the function for actually predicting that it was panda or cat or dog by our model. So here I think that there is some issue and our model is not trained properly. That's why it is actually predicting it to be another class. Now let's actually have a look at other things. Okay, so there is some issue. Okay, so there seems some issue. Hmm. So there was just no issue other than that we was actually, yeah, accessing the one here, but instead we must actually access the zero here, because we only have one particular image here for the explanation and not many images. But it also work for any other one if we have an array of images here, and we might have to explain it for other image also. But here we only have one particular image of this panda, which is actually transformed into the URL. So we need to supply the zero as the argument, zero as the index. So yes, if we actually run this particular block, it will actually generate the random perturbations, and we will get the predictions for those. And from those particular predictions, our instance will be actually trained, or say you can say it has got the intuitions that which pixels are actually supporting the prediction. And with this particular block we can actually explain our decisions, that these were the particular sections which are actually highlighted in green, which are actually contributing positively for our panda prediction, and these were the red pixels were the one which were actually contributing negatively to our output prediction. Now, what this helps is that we can actually then fix our input data, or say we can actually fix our model to actually train it better. So this is how explanation is actually used. You actually use to have an intuition that at which pixels your model is actually looking now, so that you can actually train your model well, so that it doesn't actually fail on the real world scenarios or high stake decision where your output actually matters a lot, like a life or death situation. So here you actually are doing is the same which I explained earlier. You are actually getting the prediction from the Inception V3, which is a pre-trained model in the available in the Keras library. So it is actually downloading the stuffs here, and then it is getting the prediction, and that is the highest for the giant panda, as I explained earlier. And now you need to explain, so you can use this particular block for the explanation, and it is again generating those number of pixels which we have mentioned here, that is 1000. And it will get the prediction from the Inception V3 model for every image, and then accordingly it will gather the pixels which are available out there for the same. So yeah, it is actually doing it in a slow rate. Okay. So yes, so it is actually showing that these were the pixels which were there for predicting our output class to be a giant panda instead of other ones. So in the first one, which is actually the first one, you are actually showing that with these parameters, and in the second image you are actually showing the same image but with these parameters. So it is actually showing you the different aspects of the same results. In the previous one you are actually showing only those features, and other ones are actually switched off. And in this one you are actually showing the both ones, but you are actually highlighting the positive contributing and the negative one separately. So this was a basic of the Lime explanation using the image dataset. Sorry if I actually explained something wrong, but this is actually just the intuition that how a newbie will actually try to interpret or say interpret a model for explanation with the image dataset. Thank you so much.